Okay, so we've talked about some folds and some faults, and now we're going to look at something much more complex. So instead of just our separate folds, so we have an anticline, we have a syncline. Remember, we're thinking about, I think what's more valuable is to think about a rug that you're squishing from the side, so you have ups and downs and ups and downs and ups and downs. That's what we get in mountain building zones, like Pennsylvania. So this is near the Suwannee River of Pennsylvania, and we have a really complex underlying structure. It's complex, but it shows up in so many different geology textbooks because while it is kind of while it is kind of complicated from our 100 level geology perspective, it's pretty clear cut to geologists who are like, whoa, that is definitely a nice anticline, nice syncline. And a cool part is, and if you take a structural geology field trip with us at NKU, where we actually go to, I think it's called Bear Valley, Pennsylvania, some of these, we don't just have a flat surface here. Some of these are uplifted and exposed, and you can actually see you could just sit on an anticline and be able to see that. So that's pretty neat. So it's not necessarily flat like that. It's definitely not, because it's a very mountainous part of Pennsylvania. Okay, but how do the mountains form? Is the anticline going to be a mountain and the syncline going to be a low valley in between mountains? No, it'd be nice if it was like that, and maybe it was back when this first started forming 250 million years ago when the Appalachians were coming together, but even then erosion would have been taking place, and especially since then, lots of erosion has taken place. So, nah, that's not what's happening. What is going to be, and I'm just procrastinating because I know drawing on this is going to be very challenging, but I want to tell you what is really happening as far as mountains go. What it's going to be is where the more resistant layers of rock are exposed, and the softer, less resistant layers of rock are being exposed. So while we have all this pressure and mountain building going on and continents colliding, we're still dealing with erosion. We're still dealing with rivers carving down through these rocks, maybe glaciers scouring things out, So as we have, let's say that in this case, the pink layer of rock is really soft. Let's say it's a limestone or something that's really soft and gets eroded away pretty readily. That means that even at the very top of this anticline here, where the pink rock is exposed at the surface, we may have a low area. We may have a low-lying area, and this may form a valley. What if this kind of tan, yellowy tan layer was really hard and resistant, like a layer of sandstone? This may stick up above the landscape. So then you'd have one mountain, a valley, another mountain, whatever's going on over here. You may have several mountains with just a couple structures. So erosion is going to add another layer to the complexity of these types of folds, or any type of fold. Okay, but you can probably see, now that I've mentioned it as well, but you can probably tell from the side, we have an anticline and a syncline, and beginning to build back up to another half of an anticline. Just like taking your rug and squishing it and having ups and downs and ups and downs, and that's what mountain belts are all about. So what I'm going to do is start to draw some symbols on this, and this is definitely a much more complex picture, but I really, I think it's really cool because it shows you a bit more of what geologists are actually looking at. Something like this, not something like that so much. There are some special places where this sort of simple diagram can show up, but if you look at a geological map of a mountain belt, it's going to look quite like this. Well, how on earth could you make sense of that? Well, let's not even look at the side for right now. Let's just look at the top. And we can see that we have repetition. That's the first thing to look for. We have repetition. Where are our mirrors? Where are our axes? We have one here. Okay, so this is kind of pointing, and we can see that we have a repeat of layers on one side versus the other. That pink layer is doing the same on that side as on this side. So that's an axis right there of a fold. Same thing right here. There's an axis of a fold, and right there. We've got 3 folds going on here. One of the things that is different about these folds, though, is instead of parallel bands of rock just going straight back and having the same amount of exposure on the surface all the way back, like our nice simple non-plunging anticline here. In this case, these beds are plunging, which means that not only do we have beds dipping away from and towards the axis on the ends, but if we turn it toward the side, The whole structures are plunging, and they're plunging, remember here, right? This way. So towards you. So all these beds are plunging towards you, which means that we don't have these parallel bands of rock exposed to the surface. We have these V shapes instead. And that's very special and, again, very common because you could probably imagine that, okay, if you already have enough stress, enough compression to get all this ups and downs and ups and downs, chances are good you're probably going to have an up on one end of the axes and a down on the other end of the axes, and probably the whole thing's going to be plunging, and it is in this case. So, okay, now I'm done procrastinating. Let's see if we can draw some things now. Okay, so we're going to find out where our anticlines and synclines are. So here's our anticlinal fold. One of the ways I know this is an anticlinal fold, to put the paint down again, is check out the side here. This pale gray, which shows up in the very center, oh, that's an anticline too. We've got two anticlines with a syncline in the middle. Up, down, up. That's what we're looking at. This light gray layer is the oldest rock exposed at the surface. This dark gray stuff is never exposed in our map. The light gray stuff is. It's exposed all the way back here. But because it's the lowest most layer, we know it's also the oldest. So we have oldest layers of rock in the middle with progressively younger layers out to the sides. That's how we know that's an anticline. You're probably wondering, what does the other end look like? Well, because this whole thing is plunging, the other end just looks like this, where we have a lot more of the older rock uplifted and exposed, and we're not seeing a whole lot of younger rock here. The younger rock is definitely on this end, because the whole thing's plunging now towards me, away from you. Okay, so we know that's an anticline. So let's go ahead and draw an axis. I'm going to draw it here. I don't want to draw it right in the middle because it's kind of off the thing. But let's go ahead and draw it right here, our little axis. And again, to form an anticline, as you can see over here, the beds, just make sure I'm right, the beds are dipping away from the axis, right? They're dipping down away from the axis. Remember, dip is about pointing downward. So our symbol for an anticline is, again, arrows going outward, just like that. And we could do some strike and dips, except in this case, I'm going to put it on the pink layer there because it shows up in a lot of places. In this case, the strike is not, well, actually it's kind of close here, but it's not necessarily going to be parallel. So here, our lines of strike were parallel to one another. They were the same direction. They're both pointing north or whatever, because this is a non-plunging fold. But this is a plunging fold, so the lines of strike actually may, they're not exactly away from one another. Neither is dip. Okay, then we could go ahead and do that here. We could draw the same thing. I'm not going to bother with strike and dip so much, but we could draw our anticlinal symbol. And again, remember what we're doing here as geologists. Well, hell yeah, I'll do that too. As geologists, we are looking at a map view. We're not going to draw anything here because no one's looking at this. No one's seeing this necessarily. They're looking at a geologic map, a bird's eye view image, and having to read symbols that tell them what's going on. Now, what I could do is I could have a little text box here. I could write, hey, this pink bed is dipping toward the southwest at a 30-degree angle, something like that. But I'm maybe communicating with people who, maybe they're not using English. Maybe, that's just a lot of writing. You don't need to do that. All I need to do is this, to show what that pink layer is doing. And yeah, you can't, I didn't really do this over here, but you can also put the direction. So the angle of dip. So if my angle of dip here is, say it's about 35, 40 degrees, I could actually write 40 degrees there too. So that's something that you see a lot on geologic maps. So anyone who's walking around on the surface knows exactly what those beds are doing below the surface. Okay, now let's do our syncline. Oh, we're already partly done though. Check it out. The anticlinal strike and dip symbols, they're facing away from the axes of the anticlines, but they're facing in towards the syncline, right? Okay, now I just need to draw my syncline symbol on the blue here, And again, you could tell it's a syncline from what's going on the end, but even if we didn't have that, we know that this is a syncline because the blue layer is the youngest in our map. And we are just going to draw arrows pointing in towards it. We already have our strike and dips. We already have our dips pointing in towards this, so we don't need to draw any more strike and dips. All right, so it's definitely looking a little more complex than just our simple fold, but this is what the Earth does, is what real life looks like, is definitely some more complex things like this. And again, if this pink layer is nice and hard and tough rock, but the blue layer is nice and, actually that was not a good example. If the pink layer is nice and soft and easily eroded away by rain or rivers, whatever, and the blue layer is a really hard, tough, solid sandstone, then even though this is a syncline, this blue layer could stick up above the landscape and the pink layer could be, eroded pretty deeply down and be a valley. So this is the heart and soul of what's going on in mountain building to begin to create those fantastic landscapes that we see with mountains. But it takes erosion to carve down through these features and expose different layers of rock. Because if we didn't have erosion, we would just have, what's the youngest layer of rock in here? It's the blue one. If erosion wasn't taking place, we would just have the blue layer doing this. And we'd just have layers going all the way down. We couldn't see them. Erosion has to cut off this and so we can actually see what's going on. So as opposed to a kitchen rug that we're squishing and we get ups and downs, what we're actually kind of doing is taking a stack of kitchen rugs of all different colors and ages, squishing them, and then taking a chainsaw, carving through it, looking down, bird's eye view, and seeing all this repetition of those layers exposed at the surface of this thing. That's not a bad example. That could be a good activity to do to really show you what's going on here. Oh, I'm sorry, I did forget a symbol. These are plunging folds, so they also have to show you the direction in which they plunge. Synclines is kind of a rule. Plunge in the direction in which they open. So I have to draw a little arrow here to show that the axis is plunging. I know that, and I cheated because I remembered that what the side is doing here. So yeah, the whole structure, all of these guys, both anticlines and the syncline are all plunging toward you. Let's say that's to the south or whatever. Anticlines are doing the same thing. We're not going to get flipping around or anything crazy like that. They're all plunging in the same direction. So my arrows are all going to be the same. The only difference is that if we were at the surface walking around and we saw this and we knew this was an anticline, anticlines plunge in the direction in which that V points. Synclines plunge in the direction in which the V opens. Okay, so that's kind of a rule. So anyway, so now our image is complete. I could put strikes and dips on all of these. I could put angles, like this one's dipping at 30 degrees, this one's steeper, maybe 45 or 50 degrees. I'm not going to deal with any of that. But that's basically, that's a good way to communicate to anyone using a map. If the map was printed like this, which there are, check out the Pennsylvania geological map, and it's got something just like this on it. Then you're communicating to other geologists exactly what those beds are doing. So anyway, I hope this was helpful. I think this is some of the most challenging stuff in all of geology. It's only been through teaching this for years that I've really got a handle on it. So, what you guys will have to do on the exam is basically recognizing these things and answering some questions about them. So recognizing the difference between an anticline, syncline, normal fault, reverse fault, all those things. Talking about the type of stress that caused it. Talk about, okay, where are the youngest beds exposed in an anticline versus a syncline? Things like that. So you won't have to draw on anything because, it's just, a little too challenging with our online labs right now. But anyway, hope that was helpful. Gave you a little appreciation for how complicated this can get in mountain building systems and the importance of understanding what's below your feet as far as dealing with water resources, coal, petroleum, mining for all sorts of metals. Structural geology is a hugely important field to help us know what's under our feet and is it feasible to get it out so we can use it. Oh, and my counter. Now that I have this, I wanted to show you, since we were talking about metamorphic rocks over the past week or so, my counter here is a rock that you probably recognize from your metamorphic rock lab. This is a rock called gneiss. And this is a perfect example of ductile deformation. So I could have two different colors here, and it could be a really good example where it's kind of like mixing two different colors of Play-Doh together. But remember, with gneiss, you have that gneissic banding where the mafic or black minerals separate out away from the felsic or white or pink minerals, and you end up with this kind of zebra or tiger striping going on. So a really good example of rock that forms from very, very high heat, very high pressure, deep in the heart of a mountain system, and is quarried and is used in countertops and stuff like that. So yeah, not granite. Most countertops, maybe not most, but a lot of countertops are not granite. If it has anything kind of swirly or stripy like this, it's a metamorphic rock, not an igneous rock. So same minerals pretty much, your feldspar, hornblende, quartz, all that, nice, tough, durable minerals, good for a countertop, but it's good to actually know what you're looking at and be able to appreciate it. This was formed in the heart of a mountain system, and that's very cool. All of our metamorphic rocks they tell us a huge story about the earth that other rocks just can't quite do. So, and the more I learn about it, the more excited I get. So anyway, hope that was helpful for you. Thanks, guys, and enjoy learning about rock deformation. Thanks.